Do you hear me, my
Yes.
student?
Yes.
We can.
Yes.
Yes, sir.
Yes.
Yes.
Okay. Uh, Sorry. Have you seen my screen?
Yes, we can
Yes.
see it.
Okay. Okay. So, first of all, I like to excuse you. Ask you to excuse me for last Saturday. We have a very long class. So, and some of you asked me to slow down the speed. So I will try to do it today. But anyway, as always, I will give you some review of what we studied last week. And last week we study that things that is some operation on matrices. And the first one, the matrix is something like that. What you are seeing on the screen, that is a rectangular table consisting of number. It is divided into m rows and n columns, and each entry is a, I, j, lying on the i's row and j's column. It is a real number. In case m equal n means it has the same number of rows and columns. We call it a square matrix. And special square matrix is a diagonal matrix, usually denoted as here. That is a square matrix will have zero everywhere except those lying on the main diagonal, like in something in the red route here. And we define that two matrices A and B are equal each other if, first of all, they must have the same size n by n, and then the corresponding entry must equal each other. Means we have A ij equal B ij for any I and any j. With that, we can define the matrix addition. In Vietnamese is phép cộng mà A and B are of the same size m by n. Then A plus B is a new matrix of the same size m by n. And the entry of the sum A plus B, please switch off your microphone, please. Then the entry of the sum A plus B equals the sum of correspond entry of A and B. And that is the first operation on matrices, and it is very easy for you to calculate. And we have some examples during the class, and I believe that in your tutor class also you have a chance to practice calculating on these things. And also the next one is the scalar multiplication. Means if we are given a matrix A of any size m by n, and C is any number, and we call it a scalar, then the multiplication C A or A multiplied by C, that is a new matrix of the same size, having the entry is obtained from the corresponding entry of A by multiplied by the number C, like the formula on the screen. And with that, we can define the matrix subtraction, phép trừ các ma trận. A minus B equal A plus minus 1 multiplied by B. So that is a C operation for matrices, and it's very easy. And the most difficult operation, that is a multiplication of matrices. Suppose that you are given two matrices A and B. Please be careful with the sign of A and B. Here A is a matrix standing on the left, and B is a matrix standing at on the right side of A. Or we say A is the first matrix and B is the second matrix. Then we require that the number of columns of the first matrix must be equal the number of columns must be equal the number of rows of second matrix. Means here, if you look at the small red arrow, you see the number of column of A equals the number of rows of B, and the bigger red arrow will show the sign of the product here, like that. So you see, in case we have the number of column of A equals the number of rows of B, we can multiply them together like that. And Cij, the entry of product, is given by a formula like that one. The formula is complicated, but however, if you look at the picture at the bottom of the slide on the screen now, you see it is not so difficult to remember. And also, if you look at here, you will understand the requirement about the number of column of A equals the number of rows of B because of the formula here. And here are some property for matrix multiplication. We have 1, 2, 3, 4. The first one is associativity. The second and the third is distributivity. One is on the left and the other is from the right. And number 4 is saying that CAB equals CA multiplied by B or A multiplied by CB. In the property number 4, please be careful that C here is a number, not a matrix. The small c here is a number or scalar, but not a matrix. If you put here is a matrix, it will be a wrong claim. And the last property, and it is not property, but that is a remark. In general, you don't have A multiplied by B equal B multiplied by A. Means the matrix multiplication does not have commutativity. You cannot exchange two matrices in a product. And in the class on last Saturday, we have a series of examples about that. And the next operation, that is about inverse of a matrix. Now the first definition saying that if A is a square matrix, we say that A is invertible if we can find a square matrix B of the same size, satisfying that A multiplied by B equal B multiplied by A equal identity. In that case, B has names the inverse of A. And in case a matrix A does not have an inverse, means that we cannot find a matrix B satisfying that equality. We say that A is a non-invertible, or we say A is a singular matrix. And if such a matrix B can be found, it means the inverse of A can be found. It will be unique, and because of that, we always denote it by A to the power minus 1, and we call it A inverse. Then the equality here will becomes A multiplied by A inverse equals A inverse multiplied by A equals identity. I'm sorry, I forget to do something. Yeah.
Recording in progress.
Yeah. The inverse of A is unique, and we denote it by A inverse like that. Okay. Now, suppose that you are given a square matrix A. One of your exercise, that is you need to find the inverse of A. So first, you need to decide if A is invertible or not. And in case A is inverse, you need to find its inverse. How you can do it? And last Saturday, I explained to you and through some examples. That is, we can use Gauss-Jordan elimination to do it. Here, I summarize it in 3 steps, like you are seeing on the screen. First, we write the identity. We write the matrix A, and on the right side of A, we write the identity matrix of the same order here. Then, the second step, we will use elementary row operation in Gauss-Jordan elimination procedure to reduce the matrix A became the identity. Then, by the same operation, the identity matrix here will become something, and that something is exactly the A inverse here. So that is the procedure to find inverse by inverse of a square matrix A by Gauss-Jordan elimination. And I show you an example here. Usually when I review the class of the previous week, I never show the examples. But today I show you these examples. Why is that? Because I want you to remember the notation for the elementary row operation here. And because we are going to use that in the class today. Now suppose that A to be that 1, A to be that 1. And the first step, I write the identity matrix I on the right side of A. And because of that, we get nothing. We begin the Gauss-Jordan elimination by nothing. That operation means we multiply the first row by -2 and we add that to the second row. It means that we need to make that become 0 and we get nothing. The first row is unchanged, the last row is unchanged, but the second row now became nothing. And correspondingly, the identity part now becomes nothing. We continue this. We continue the Gauss-Jordan elimination by applying that operation. That operation means we multiply the first row by 6 and we add to the sixth row and we get that one. And the second part, I mean the identity part here, now becomes that one. And again, we continue it that way. We apply that operation. That operation means we multiply the second row here by 4 and we add to the third row. Then it makes that entry become 0 and you get nothing. It is almost now, the A part now is almost identity. We apply that things first. R3 to the power -1 means we multiply the third row by -1. It will make that entry becomes +1, not -1 like that. So we get that. We continue this on the next slide. You get that one. And it is the left only one thing here. We need to make it become 0. So we get that one. We apply that operation. That operation means you multiply the second row by 1 and you place plus to the first row and you get nothing. Now that part is already is identity. And on the second part, you need second part, you get that one. And that one, by our method, we know that part is exactly A inverse. Then we say the matrix A is invertible. And its inverse is exactly that one. And you can verify it by multiply them, and you get the identity matrix here. So in this slide, I show you an example. The example is about using Gauss general elimination to find the inverse of a square matrix. But however, what I want you to remember, that is only the notation for the operation here. Let me continue the revision. After define the inverse and the matrix product, matrix multiplication, now we define the power of a square matrix. Suppose that A is a square matrix, and we define A to the power 0 equals identity. And then for any positive integer k, we can define A to the power k equals A multiplied by A multiplied by A k time. We say k factors of A like that. And similar to the property of power of any number, we have the property number 3 like here. And you can read it on the screen. I will not read it here for you. Just only the property number 4 saying that in case D is a diagonal matrix, the D to the power k is very easy to compute. If you have some question, please write it on the chat box, and please switch off your microphone now. Here D to the power k to be like that. We take any entry lying on the main diagonal and take it to the power k, and you get the reason is here. And here is a property of inverse of some matrix. Suppose that A is an invertible matrix, k is any positive integer, and C is any non-zero scalar. Then we have the following property. Property number 1 saying that A is inverse, then the inverse is invertible, then A inverse is also invertible, and we have that formula. Means if we take inverse 2 times, you will go back to the original matrix A. And if A is invertible and k is any positive integer, then A to the power k is also an invertible. And then the inverse of A to the power k is exactly the product of A inverse k times, like that. And because of that, we usually denote it by A to the power minus k. Now, if C is a non-zero number, then the scalar multiplication CA is also invertible, and its inverse CA inverse equals 1 over C multiplied by A inverse. And by that, you will understand why we require that C must be non-zero, because otherwise we cannot write 1 over C. And next property saying that if A is inverse is invertible, then transpose of A is also invertible, and inverse of transpose of A is exactly the transpose of the A inverse. You can verify it by yourself. And the property number 5 saying that A and B are invertible matrices of the same side n. Then the product AB also is invertible, and we have A B inverse equals B inverse multiplied by A inverse. You should note that the order of AB on the left hand side and the order of them on the right hand side is changed. on the left hand side A comes before B, but on the right hand side B inverse comes before A inverse. So that is something you should note. And it is somehow similar to the transpose, similar to the that property for transpose of a matrix. Next, we are saying about the property of invertible matrix. If we have the property 6A saying that if AC equals BC and C is invertible, then we can imply that A equals B. It means that we can cancel C on both sides of the equality here. Because of that, we say that is a right cancellation property. Similarly, we have a left cancellation property saying if we have CA equals CB and C is invertible, then we can cancel C on both sides to get A equals B. Property number 7 has named Cramer's rule. It's saying that suppose that A is an invertible matrix, then the system of linear equation AX equals B has unique solution, and that solution is given by the formula X equals A inverse multiplied by B. That has named Cramer's rule. We are going to apply that today or maybe next week. That is some of application for determinant. And for anything, we summarize in the following. Property number 7 prime. If A is an n by n matrix, a square matrix of order n, then we have the following claim which are equivalent to each other. A, B, and C. Equivalent means if we have A will imply B, B will imply A, B implies C, and C will imply B. So, three equivalent claims are as follows. The first claim saying A is invertible. Second saying AX equals B has unique solution for any column matrix B. And the last claim saying AX equals 0 has only trivial solution. That is three equivalent claim for a matrix A. And that is the end of the lecture number 2 about operation on matrix. And then we continue to study about determinant. Whenever we say about the determinant of a matrix, we always say about a square matrix, so be careful for that. And it is defined as follows. First, the determinant of a 2 by 2 matrix is very easy to define. Suppose that A equals a matrix A11, A12, A21, A22, like that. Then determinant of A is a number denoted by A between the two parallel vertical lines like that. And that number is defined by that things on the screen, you see. Then we need to define determinant for any square matrix. We will define it inductively một cách quy nạp as follow. First, we already define determinant for any 2 by 2 matrix, and now we suppose that we define determinant for any matrix of size n minus 1 by n minus 1. And we are given a matrix A of size n by n, like A on the screen here. So first, we choose any entry Aij, the Aij here. And then we delete entirely the Is row, and entirely the J columns. Yeah. After deleting those things, after deleting the Is row and J column, they left only a square matrix of size n minus 1 by n minus 1. It is here. Yeah. And because we suppose that we know already the determinant of any n minus 1, so we know the determinant of this matrix, and that determinant will be called the minor of the entry Aij and denoted by Mij, like that. That is a minor of entry Aij. If so, for any Mij, if we multiply the minus 1 to the power I plus j, then it will be denoted by Cij and has name cofactor of Aij. That is the notion about the minor of entry Aij and the cofactor of entry Aij. Now we can define. Then if A is n by n matrix, the determinant of A is defined by this formula. And in the formula, the index I is a fixed. The index j runs from 1 to n. And that formula has named cofactor expansion along the i's row. And you should know that I can be any number from 1 to 3 up to n. Similarly, we have another formula we call cofactor expansion along the j's column with any j from 1 to n. It is here. And again, you can see that in the formula here, the index j is a fixed. Only the index I runs from 1 to n. That is the reason why we call it the expansion along the j's column. In the class last Saturday, we have several examples to compute determinant. And here, I just only tell you one practical way to find determinant of any matrix of order 3. And it is here. Very, very easy, but however, not so easy, but it is very practical for you to remember when you try to find determinant of any matrix of order 3. Last thing we studied last week is the determinant of a triangular matrix. Definition of triangular matrix is on screen. We have an upper triangular matrix and the lower triangular matrix. And if something is upper and lower triangular matrix at the same time, it is exactly the diagonal matrix we define from the very beginning of the class today. And we know that here is some examples about the upper and lower and triangular matrix and the diagonal. And last Saturday, we stopped at this point. We say that if A is any triangular matrix, it can be upper or lower, or even it can be a diagonal matrix, then the determinant is very, very easy to compute. That is, it is a product of all the entry lying on the main diagonal. And it is given by the formula on the screen here. And today, we will continue from this point. So, Have you seen my screen now?
Yes, we can.
Yes.
Okay.
Yes, Professor.
Here, last week we stopped at this point. So now first I would like to give you some example about that one. Now you are given two matrices like that, A and B. You need to find their determinants. First, I take a look at the examples number A. If you use the definition, use the cofactor along the first row, the first row here has only one non-zero entry, that is the number 2, and all other entry are 0. So we can expand along that things you get that one. It will determinant of A will be 2 multiplied by determinant of the matrix in the red box is here. And again, the matrix in the red box is an upper triangular matrix, and even you can expand it along the first row here, and it has only one non-zero entry is here. So you get, once again, it will be -2 multiplied by the small one here. And finally, you get here. Determinant of A equals 2 multiplied by -2 multiplied by 1 multiplied by 3. And the reason is -20. Similarly, for that thing, that one is not only triangular matrix, but it is also a diagonal matrix, and its determinant is that one, the product of anything lying here. So that is our examples. And now I will show you another way to evaluate or to compute determinant of any square matrix, and that method using the so-called elementary row operation. So I recall you, for A is any matrix, not only square matrix, but also I repeat, in this lecture, in this chapter about the determinant, we always deal with square matrix. So here I say A is a square matrix. We have 3 kinds of row operation as follows. The first one denoted by Rij, like here. The second is Ri to the power k, and the next one is Rij to the power k. And we define it already, and in the tutor class you know it already, so I require you to remember the notation here. Now we give a definition of what we say elementary matrix. The elementary matrix is denoted by the same letter like here, but it's the bigger one. So instead of small a, we use the capital A here. Rij means we apply the first operation on the identity matrix. The second one means we apply the small Ri to the power k to the identity. And the last one, the capital Rij to the power k, means we apply the small operation Rij to the power k on the identity A. And those three matrices will be called elementary matrices. Usually we don't denote it by E. The letter E stands for elementary. We say that is we denote it by E in case we we didn't to distinguish between the three elementary matrices. Now your homework number 1. Please verify that if you take the first elementary matrix and you multiply by A, it equals, you apply the first operation here on the matrix A. And then if you multiply the second elementary matrix by the matrix A, it equals, you apply the second kind of operation here on the matrix A. And the last one, if you multiply the third kind of elementary matrix by the matrix A, it equals, the reason equals that you apply that operation, the third operation here on the matrix A. And in order to see that, I write it here, but however, it is somehow easy for you to see. Now I will write down what is Aij, what is Ai to the power k, what is Aij to the power k. That is a three elementary matrices is here. First, identity matrix is here, and I pay attention to the one here and one here. That is the entry lying on the I's rows, I's column, and J's column, J's row and J's column. Then the first elementary matrix will be here, because we exchange the I's row and I's and J's row. Then that entry will go here, and this entry will go up there. And because of that, we get 0 here and 1 here. Similarly to that thing, 1 will go from here to there, and the other entry will go 0 will go from here down there. We get that thing. So please turn off your microphone, please. Some of you, please turn off your microphone. I continue here. The next will be here. If you multiply the I's rows of identity, you will get that will be k, and any other entry unchanged. And the last one is here. Aij to the power k means here is 1, here is 1. And when that point will be k. And it is very easy for you to verify it. Now I write it for you to see the form of elementary matrices. Now we continue how we can use elementary row operation to find determinant of any square matrices. Suppose that A and B are two square matrices, and more than that, if B is obtained from A by applying Aij, then determinant of B equals minus determinant of A. And we can say that in a square matrix A, if we exchange two rows, then the determinant will be changed by the sign. In Vietnamese, sometimes you see, if you, I don't know, if you have a Vietnamese textbook, it says that trong một ma trận vuông, nếu chúng ta đổi chỗ hai hàng thì định thức đổi dấu. That is what it says. And next, suppose that B is obtained from A by applying that, then determinant of B equal k times of determinant of A. And the last one, if B is obtained from A by applying Rij to the power K, then determinant of B equals determinant of A. And it means that here, I summarize it in the bracket here, and you can see three things here. And here is an example. Suppose that A is that matrix C by C. And suppose that we know already that determinant of A equal minus 2. And very easy for you to compute it. And if you are given A1, A2, A3 like that, and you are required to find determinant of A1, of A2, and of A3. How you can do it? The first one, we observe that A1 can be obtained from A by multiply the first row by 4. Then it means that A1 equals A1 to the power 4 of A. And because of that, we obtain determinant of A1 equals 4 times of determinant of A, means it equals minus 8. Next, A2 can be obtained from that by exchange two rows. The first row now go here, and the second row now going to the first row. And because of that, the determinant will be changed by sign, means that determinant of A2 equal 2. And the last one, you see, the last one is just a little more difficult to see. A3 is obtained from A by multiplying the first row by minus 2 and add to the second row. And because of that, the determinant of AC equals exactly the determinant of A, and it is a minus 2 here. So now we summarize it. On the in the previous slide, we know already that one. Then it implies that thing, and I put anything here in a red box. That is what I summarize. I denote it like that, and I call it property number B. That is a property number B. Now, I am going to show you that we can use property number B to find determinant of any square matrix. How we can do it? We need two observations. The first observation saying that the row echelon form of a square matrix is always upper triangular. Row echelon form of a square matrix, row echelon form of a matrix, you know what it is. But if it is row echelon form of a square matrix, it is upper triangular matrices. And the second observation is most important thing. That is, if you use elementary row operation, you can always transform any square matrix A into row echelon form. With two observations like that, you see that now you can compute the determinant of any square matrix. I summarize the methods in 3 steps as follows. That is a method to compute determinant. The first step, we use elementary row operation to transform the square matrix A into row echelon form. That is the first step. The second step, that is because row echelon form of a square matrix is upper triangular. Then for upper triangular matrix, we can find the determinant. The determinant of triangular matrix is very easy to compute. it is a product of all the entry lying on the main diagonal. Then the last set, we use property P. The property P in the red box, and we can compute back to know what is the determinant of A. We summarize it in 3 steps like that, but now we look at an example. Here, suppose that we are given A like that. You need to find determinant of A. How we can do it? The first one, we apply A1, 2, means we exchange the first and the second row. We get that one. And because when we exchange two rows, the determinant will be changed by sign. So we put minus here. That is written in the property P in the red box. You can verify it. Next, we apply that one. A1, 2 to the power minus 2 means we multiply the first row by minus 2 and you add it to the second row and you get nothing. And because of that, the property P saying that if we apply that one, the determinant is unchanged. So that will be equal to that one. Once again, now we apply A2 to the power minus 1 over 7. You get nothing. You get nothing. And we continue it by applying that operation. Multiply the second row by minus 1 and 8 to the third row. You get that one. Now is already the row echelon form, and row echelon form now is an upper triangular matrix, and that the determinant of that now is very easy to find. It is minus 7. That is examples for you to see. So I think that we should take a short break now in 5 minutes, and then we can continue, please. Have you come back already?
Yes.
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 Okay.
Yes.
Okay. Please let me remind you that if some of you have your microphone, please switch it off. Otherwise, it can interfere the class. If you have some opinion, some question, please raise your hand or put it on the chat box, and then we can answer it. Please don't interfere my lecture. Now, before the break, I explained to you by examples how we can use the elementary row operation to find determinant of any square matrices. The next slide will show you something. That is the property saying that if E is an elementary matrix, you should remember that we have a C kind of elementary matrices, and C kind of elementary matrices corresponding to C kind of row operation, and also the same notation, except the one is small, the operation is small, and the elementary matrix is the capital or the big one. And now the property is saying that if we take any elementary matrix and multiply by a square matrix A, then determinant of the product will be equal the product of determinant of E and determinant of the matrix A. And I can show you by the following way. Now, first, because we have a C kind of elementary matrix, so we will consider each kind. The first one is E equals the first kind of elementary matrix Aij, like that. I gave you the form of Rij, so we know exactly that in that case, determinant of Rij or the determinant of E equals -1. You can look back at the slide I up on the model. You will see the form of Rij will give you it has a determinant is -1. Now, because according to your homework, A multiplied by A, E multiplied by A is exactly, you apply the operation Rij to the power A, to the matrix A. And because of that, that equals -1 A. But -1 is exactly the determinant of Rij. So you get it here. So for the first kind of elementary elementary matrix, we have that equality. Determinant of the product equals the product of two determinant. And so on, you can apply the second one. If E is Ri to the power K, then determinant of E will be K. And in that case, we use the similar things here, you will get that one. And so on. I will leave it for you to read by yourself, but anything is very easy. Everything is written clearly here. And the last one, again, you have the determinant of E in the last time will be 1. And because of that, you will see nothing. The key point here is your homework number 1. The homework number 1 saying that if we take the elementary matrix E multiplied by A, it is equals, you apply the corresponding row operation apply on the matrix A, and then anything is clear for you. I'm sorry, please wait for me a little. I have some guests coming into my office. Just 1 minute. Now, I want to tell you that is the determinant of a square matrix can be computed by using row operation. But also, because we see that the determinant of A equals the determinant of A transpose, means that in computing determinant of A, we can do similar things by using columns instead of rows. Means we can define the operation on columns but not on rows. So how we can do it? We can do it as follows. First, I recall that elementary row operation are denoted by small r like that, and it is given here. But now we can define it for columns. The columns, elementary column operation will be one of following kind. The first one, Cij, means we exchange the i's column and the j's column of the matrix A. And Cik means we multiply the i's column of matrix A by a number k. And the last one, Cij to the power k, means we adding k time of the i's column to the j's column of the matrix A. So we have 3 kind of column operation, quite similar to the 3 kind of row operation. And on those operations, we call it the elementary row operation or elementary columns operation. Now we see how we can use it. Similar to row operation, for the column operation, we have the following property. if B is obtained from C by applying Cij, then the determinant of B will be obtained from determinant of A by change the sign. It means that determinant of Cij of A equals minus determinant of A. Similarly, if B is obtained from A by applying Cik, means if we multiply the whole i's column of A by the number k, then determinant of B will be k times of determinant of A. The last one, if B is obtained from A by applying Cij to the power k, then determinant of B equals determinant of A. And we summarize it in the bracket here. And now I put that in the red box again. That is a property we are going to use in computing the determinant of any square matrix. Here is some examples. Suppose that A to be like that, and not so difficult for you to find that determinant of A equal minus 8. Now, suppose that you are given A1, A2, A3 like that, and you are required to find determinant of A1, A2, and A3. How you can do it? First of all, A1. You see that the first column of A1 is obtained from the first column of A by dividing any entry by 2. So it means that A1 equals C1 to the power 1/2 of A. And because of that, determinant of A1 will be 1/2 of determinant of A. So you get minus 4. Next, A2 is obtained from A by exchange two first columns here. The first column now becomes the second column, and the second column now becomes the first column. So because of that, the determinant of A2 will be minus determinant of A, means determinant of A2 equals 8 here. Last, A3, not so easy to see. That is, A3 is obtained from A by applying that one. Means we multiply the second columns by 3, and then you add that to the first column. So you get the new columns here. Then because of that, determinant of AC equals exactly the determinant of A, and it is minus 8 here. So that is examples about using the elementary row column operation to find determinant. So now we know we have many ways to compute determinant. You can expand it along any rows or any columns. You can use elementary row operation or elementary column operation. But there are many cases you don't have to do any calculation. You can give that the determinant is 0. So why is that? Here I give you some criteria to see if a determinant is 0 or not. And the first criterion is if an entire row or entire column consists of on 0. Any entry lying on one row, you get that one. And now you get one column consisting of only one non-zero entry, that is the number 5. And once again, you expand along that column, you get the reason. The same reason here. So, in order to find the determinant of A, you have 2 steps in calculation. The first step, that is using rows or columns operation. And the second step, you use cofactors expansion. So two steps, you apply two different ways to compute the determinant. That is why we call it the combined method. The next example is much more difficult for you. Now A is a big enough matrix like that, 5 by 5, 5 by 5 matrix. You need to find determinant of A. The first step, we apply elementary row operation like that. Then we get a new matrix. That new matrix have the second column consists of only one non-zero entry is 1. Then up to this point, from here, we will use cofactor expansion along that column, and we get it equals that one. Now it is smaller than that one, but still not so easy to find determinant. Then once again we apply the column operation like that, and we get a new matrix. That new matrix has the last row consisting of only one non-zero entry is 1 here. Then once again we apply cofactor expansion here, and we get that thing. And even here you can still apply elementary row operation R to 1 to the power 1 to get that thing. Now that one is very easy to find determinant because it is here, and that is an example for you to see. If you look back from the very beginning, we have a 5 by 5 matrix, not so easy to compute the determinant. But the first one, you apply row operation. Then we apply the cofactor expansion. Then once again we apply columns operation. Then the next step is a cofactor expansion. And then once again apply the row operation. And finally the cofactor expansion. So each step we can apply which method we think that is useful for us, and it can reduce our calculation. That is what we call the combined method to find determinant. Now, the next I show you that is some property of determinant. The first property is saying that if we have a two square matrices A and B of the same size, same order, then determinant of the product AB will be the product of two determinant A multiplied by determinant of B, like that. And as I show you in several slide before, that is in case one of matrix here is elementary E, then we know already that determinant of E multiplied by A equals that. And that is some illustration of that thing. I will not prove for you. I will not show you how you can get that. I tell you the formula is correct and you can apply it in doing your exercise everywhere. And that one, the next property saying you don't have determinant of A plus B equals determinant of A plus determinant of B. For the product is okay. For the multiplication is okay. But for the addition is not true. But however, we have that one. The property I write it here by examples, but however I put it in the red letter here. This property is true for square matrices A and B of any order. And in the formula here, I made a mistake, and none of you show me that mistake, so I will tell you here. Please look at the mouse on my screen. And here, at this place, it is A21 plus B21. That is my mistake in prepare the slide for today. Yeah. A21 plus B21. Please correct it in your slide. That is, it want to say that if you have one rows of the matrix, and in that rows any entry as the sum of two terms like that, then the determinant will be the sum of two determinant like that one. And that property I write it here is for rows, but it is true if you apply that for the columns. And I just only tell you that, and you can have more example and exercise in during the tutor class. And here are some examples for you, just only to verify the property. Suppose that A to be that and B to be that one, and you are required to find determinant of A, determinant of B, and determinant of A and B. And for A, you will find that determinant of A equal minus 7, and B will have determinant 11. And if you multiply A and B, you will get a new matrix here, and that new matrix has a determinant minus 77, and it is exactly the product of determinant of A and determinant of B, because determinant of A is minus 7 and determinant of B is 11. So you multiply them together, you get minus 77. So that's it. The next one is following. If A is an n by n matrix and C is any number, any scalar, then we have determinant of C multiplied by A equal C to the power n multiplied by determinant of A. Why you can have that? It's very easy for you to see, because by definition CA, scalar multiplication of A, means any entry of A will be multiplied by the number C. And because of that, if you look at the cofactor expansion, any term in the sum will be multiplied by Cn. And because of that, we have Cn multiplied by determinant of A here. You can verify it by examples, and I advise you to try the example with the size of A to be 2 by 2 matrix and 3 by 3 matrix. Then you will see everything here is very easy to imagine. And here is some example. Suppose that you are given a matrix A like that one, and you are required to find the determinant of A. And suppose that you know already that determinant equals 5. Then it is very easy to see that A is a 10 times of the matrix here. It is any entry here are 10 times of entry here. So you see A equal 10 multiplied by that one means here. So by that you will see determinant of A equal 10 to the power 3 of that determinant, and 10 to the power 3 is 1000, and that determinant is 5, so we get 5000. So that is an example for that property. Now I am going to tell you one more thing about the invertible matrix. A square matrix A is invertible if and only if it has non-zero determinant. So going back to the notion of invertible matrix, I know that for you, one of not so easy kind of exercise, that is, given a square matrix A, you need to find its inverse. But sometimes they require you only please then that if some square matrix is invertible or not, then in that case you don't have to apply the Gauss-Jordan elimination to find the inverse. It costs you a lot of calculation. Here, that will give you some criteria to see if A is invertible or not. And it is said that A is invertible if and only if the determinant of A is non-zero. So why that? I'll show you very easy. First, let's consider the I to be the identity matrix, and because of that, I is a diagonal matrix, the diagonal, and on entry lying on the diagonal 1, and determinant of the I will be 1 because it is a product of 1, 1, 1, 1 multiplied together. So we have I. Do you have some of you have something to ask or
No.
so please switch off your microphone, please. Now I is identity matrix, and we have its determinant to be 1. Next, suppose that A is invertible. A invertible means we can find A inverse, A to the power minus 1, so that A multiplied by A minus 1 equal identity. Now we compute the determinant of both sides. On the left hand side, it is the determinant of the product A and A inverse. And because that one is a determinant of the product, it will be the product of two determinants. Means determinant of A multiplied by determinant of A inverse. It must be determinant of the identity. And that determinant of identity is 1. We know already. So we have a product of two numbers equal to 1. It means that any of those numbers cannot be 0 because 0 multiplied by any number must be 0, not 1. So you see, first A will be invertible if and only if the determinant of A is non-zero. And here is some examples for that. Suppose that you are given two matrices A and B like that one, and you are required to decide which one is singular and which one is non-singular. Singular means it does not have an inverse, and non-singular means you can find an inverse. And here we can try. You can compute determinant, and because determinant of A is 0, 0, so it means that A is a singular, or A does not have an inverse, and determinant of B equals minus 12. It is a non-zero, means that B has an inverse, or B is a non-singular matrices. Then more than that, if A is invertible, then the determinant of A inverse will be 1 over determinant of A. That you can imply from the previous slide. So I will not repeat it here. And one more property saying that if A is a square matrix, then determinant of A transpose equals determinant of A. That we say from the very beginning of the definition of determinant. That is because we can expand determinant along any rows or any columns, and the role of the row and the column are the same. So it means that determinant of A transpose equal determinant of A. And here another example, A to be like that, you need to compute determinant of A inverse and of A transpose. And first of all, determinant of A equal 4. Then determinant of A inverse will be, because of that, it will be 1 over determinant of A, means it is 1 over 4. And for the exercise or for the example number B, because of that things, we know that determinant of A transpose equals determinant of A, and it is a 4. So it is very easy with this kind of exercise. Now I summarize that things. We have some equivalent condition for non-singular matrix. Non-singular means invertible. A square matrix of order n will be a square matrix of order n. Then we can have following claim. Please switch off your microphone, please.
Lúc đấy nó bắt đầu hết
Huyền Ninh.
Làm ơn tắt mic ạ. So I repeat it here. Suppose that A is a square matrix of order n. Then we have following statement are equivalent. The first one saying, the first claim saying that A is invertible. The second claim saying that the system of linear equation AX equal B has unique solution for any column matrix B. The third claim saying that AX equal 0, that is a homogeneous system of linear equation, has only trivial solution, means the solution consisting of on 0. 1, 2, and 3, we have it already, and I repeat it for you today in my review of what we studied last week. That is the property number 7 prime. And now we have a new one. That is the first claim, which is equivalent to the 3 above. That is determinant of A is non-zero. Means A is invertible if and only if determinant of A is non-zero. AX equals 0 has only trivial solution if and only if determinant of A is non-zero. And also AX equals B has unique solution for any right hand side B if and only if determinant of A is non-zero. And we are going to use the property number 3 and number 4 in next week, not today, but in next week we need to use that. So please remember that one. And here is some examples of we can using what we studied in the previous slide. Suppose that you are given two system of linear equation like that on here, and you are required to see which one is which one has a unique solution and which one is not. And now we can do as follow. For the system A, we write it in the matrix form like that, and the coefficient matrix A has a determinant 0, means it does not have unique solution. It does not have unique solution. And for the system number B, the matrix form of that is Bx equal B, and the B now, that is a coefficient matrix, has a determinant minus 20. It is a non-zero, means that the second system of linear equation here has unique solution. That is an example of here. And the class will stop today here, and next week we will continue with the notion of eigenvalue and eigenvector. And as I told you, we will use the property number 3 and property number 4 in doing that, in study eigenvalue and eigenvector. So please please review on what I tell you today. And now I take a look in the chat box. Some of you tell me, okay, you have new assignment given by Miss Huyền for you. Let me tell you, some of you asked me about the assignment for the whole class. Some of you asked me if it will be marked, it will be grade, and how you can contribute that, how you can use the grading, how you can see the answer for the assignment. I answer you as follows. The first one, any assignment you have to do it, and also it will be graded by us, by our lectures, and all of your answer on your assignment solution will contribute to your final mark at the end of the course. And if you want to have the answer for the assignment, you can ask your teacher in the tutor class, and they will answer you. And once again I tell you, on the assignment given for the whole class, it is very easy. It has a duty to help you to revise on the notion you study in the class. Whenever you understand the notion, the definition, then it will be much easier for you to do your exercise. That is what I want to give you some assignment, and I ask you to do it and submit it in time. Don't be worried if you forget or you lose one of the assignment, because the reason of the course, that is a process, a long process, not only 1 or 2 or 3. But anyway, if you miss on the assignment, then obviously you will get the bad evaluation by the end of the course. So that is something about the assignment. So please do it and submit it on the Moodle. So that is on what I want to tell you today. So please tell me if you have any question about the class today or about anything else, or otherwise we can stop here and see you next week.
Professor,
Yeah,
I think you made a mistake in the assignment 2.
in what?
In the assignment 2.
Assignment 2.